And in today's video, we are going to create experiment 2 using Pspice or ORCAD. So first, we will create a new project and we will name it experiment 2. And we should select analog or mixed AD and then OK. Then select the create blank project like we did on experiment 1. Click OK. And now as you can see, the workspace is loading. So now we will create a circuit that is composed of uh, is sine voltage source and a resistor. So as usual, place Pspice component, source, voltage source, and sine. Then click escape. And now we will select for the resistor. Click resistor. Control R to rotate it. And then place. Also, we should not forget the ground. So we can just simply press G and then click OK. Now we are going to connect the components to each other. So we will press W. So now we can see we can connect the resistor to ground and its voltage source. And now we will set the values for the resistor and the voltage source. So first, we will change the value of the resistor to 5 ohms. So simply put 5 and then click OK. And then for the amplitude, it's 10. We will set it to 10. And the frequency, right, we will set it to 60. So the remaining two parameters, we will set it as 0. Double click the parameter, then change it to 0. The same as with AC. Then click OK. Now everything is set. We will create a new Pspice profile. So click Pspice and use simulation profile. For this experiment, we will name it as experiment 2. Then click create. As we can see, there is a new dialog box. This is where we can set uh, the parameters for our simulation. Now, we will use the transient or the time domain, and we will show the simulation on a 1 period, which is 1 over 60, that is equal to 16.67 milliseconds. And for the maximum time step, we will set it to 10 microseconds. And now, we will click OK. So as we can see, the profile is set. So we will click this green button, the green play button, to run the simulation. schematic diagram to the simulation. To add the traces, we just simply right click, then add trace. So we will add the power across the resistor, the voltage, the waveform of the voltage, and the current across the resistor. As we can see, this is the graph uh, of those three. The green one represents the power. As we can see that uh, it never falls to the negative side of the plane. This means that there is no negative, uh, we cannot produce a negative power. This red line is the uh, waveform of our voltage source. As we can see, it forms purely a sine wave, which means that on this we can produce a positive voltage on the first half, then on the second half it produces a negative voltage. And lastly, the purple one is the waveform of the current, which is we can see it is out of phase by 180 degrees, or it means that we placed it that is not in direction with the polarity, which resulting to the inversion of the waveform with respect to the voltage source that the waveform of the voltage source produced. Here, new trace, we just simply do it again, right click, then add trace. For this time, we will plot the average power across R1. So, as we can see, this is a lot of expressions on the right side, but for this experiment, we will click AVG for this part, and then inside of the AVG, which means average, we will click the WR1, which is the power across R1. Then click OK. As we can see, this this yellow waveform represents the power across R1. As seen on the waveform, it shows that uh, the the average power is fluctuating or uh, oscillating to reach a certain number or a certain level of power that is going to produce. When we try to measure it using the cursor, at the end, we can see that the power on one cycle produces 10 watts or re- or oscillate, or it reaches the value of 10 watts. So if we're uh, mathematically speaking, it reaches the limit of 10 watts. So it means that uh, it waves back and forth on until it reaches the value of 10, approximately 10 watts. Another circuit that covers the RMS. So first, we will place a Pspice component resistor, and this time this is an inductive load. So we will add an inductor there, and then we will add a voltage source, Pspice component source. But this time, the voltage source is not a sine wave but a pulse here. And now we will put the ground. Then we will try to connect those components to each other. There, then escape. And now we will change the parameters for each component that is connected. So we will change it to 2 ohms. This inductor will be changed to 10 millihenries. And now for the parameters for the pulse, we will start uh, with the V1. So V1 is 0, V2 is 20 volts. Next is the time delay is 0. The rising time is 1 nano or 1 N. The falling time is 1 nano again. The pulse width is 8 milli or 8 M. And lastly, the spacing is, or the space of each pulse is 20 milli or 20 milliseconds. Then click OK. So now everything is set. Uh, we we can use the earlier version of our Spice Spice simulation model earlier. So we will run the Spice. So we can see it's blank again. So we will add the Spice, the traces. So add trace. This time we will add the inductor, the current from across the resistor, and then this time the RMS value, which is here says RMS, and then the current across R1. Then click OK. So as we can see, the graph doesn't says much, but we will try to edit it to increase the time stop. So to do that, close this first, then go to Pspice, edit simulation profile. So this time we will change it to 100, then and the maximum step size of 10 micro as is, then click OK. And now we can run the Spice again from our build circuit. So right click add trace, then we will add the IR1 and the RM and its RMS value, which is RMS IR1, then click OK. Now as we can see, IR1 forms most likely like a sawtooth wave, while the RMS value uh, oscillates on until it reaches a certain level. Excuse me. Um, if we try to measure the RMS value, using our cursor, we can measure that uh, our RMS value, or the current, or the effective current of our resistor, is 4.6052. This means that uh, the if uh, if we are going to measure it, this if we're going to measure the circuit using multi-tester, we can read 4.6, around 4.6, since the RMS value is 4.6, around 4.6. This means as we can see, the difference of the average value and the RMS value is that the average value averages the instantaneous values of uh, of the waveform produced, while the RMS value gets the average, then squared the mean, and then and then the squared mean was being multiplied by as and when the when the mean is squared, we will get its root, or just simply the maximum value or the peak value uh, divided by square root of 2. So for this experiment, we saw the difference of uh, these two values. Hope you like this video and see you again next time.